Okay, let's look at matrix multiplication competency 2. So here we have a matrix, and you want to find powers of that matrix, a squared, a cubed, a to the fourth, and so on, and a general formula for a to the n. So I invite you to pause this video and go ahead and do that, and I'll prepare for my part to do my part. Okay, so I hope you paused the video and did some calculations. Now let's go ahead and do some computation by hand. Of course, to find patterns, you just go ahead and calculate and see if you can see something that's regular about the result. Okay, so here I have 003. So let's multiply it by itself. And while you're calculating, you should be thinking about what's going on. Okay, so when I do this by the usual row column method, I'm going to do first row times first column is going to give me the 1, 1 entry. And notice that this is just 2 times the identity here, times this 2 times the identity. So we have 2 times 2 is 4, 0 times 0 is 0, 3 times 0 is 0. This 3 doesn't do anything, so I just get a 4 here. Let's go on to the second column, first row, second column. 2 times 0, 0 times 2, 3 times 0 gives me a 0. Third column, 2 times 3, 0 times 0, 3 times 2. It's going to give me 2 copies of 2 times 3, or 12. All right. And going down to the second row here times the first column gives me 0 times 2, 2 times 0, 0 times 0 gives me 0. 0 times 0, 2 times 2, 0 times 0 gives me 4. 0 times 3, 2 times 0, 0 times 2 gives me 0. And then 0 times 2, 0 times 2, 2 times 2 gives me, looks like that's going to give me 4. Right now, of course you can see some similarities here. Here you've got 2's on the diagonal on the original matrix. Then you have 4's when you take a squared. And then you have a 12 here. All right, so it looks like we've got some regular pattern going here. Let's look at a cubed. Okay. So here we've got, we can write that as a squared times a. So we can just do 4, 0, 12, 0, 4, 0, 0, 0, 4, times a, which is 2, 0, 3, 0, 2, 0, 0, 0, 2. And just by conventional multiplication, again looking at the patterns, this 4 goes with this 2 gives me 8. This 4 times 0 plus 0 times 2 plus 12 times 0 gives me a 0. 4 times 3 gives me 12. 0 times 0, 12 times 2 gives me 24. So I actually have 3 copies of 12, which is 36. Then next row, 0 times 2, 4 times 0, 0 times 0 gives me 0. 0 times 0, 4 times 2, 0 times 0 gives me 8. 0 times 3, 4 times 0, 0 times 2 gives me 0. Last row, 0 times 2, 0 times 0, 0, 4 times 0 gives me 0. 0 times 0, 0 times 2, 4 times 0 gives me 0. 0 times 3, 0 times 0, 4 times 2 gives me 8. All right, so let's examine the pattern here. For a, we had 3. For a squared, we had 12. For a cubed, we had 36. Right. So let's do a to the fourth and see if we can discover some pattern. So we could do a to the fourth as a squared times a squared, or we could do a to the fourth as a cubed times a. I'm going to do a to the fourth as a cubed times a. Just like to do a regular pattern. So that's going to be equal to 8, 0, 36, 0, 8, 0, 0, 0, 8. Okay. And then that's going to be times 203, 020, 0, 0, 2. All right. And if you do this, you can see that on the diagonals, you're just going to get 16 on the diagonals. And all these other entries are going to be 0, except for this one problematic entry here. And this entry here is going to be the first row times the last column, which is 8 times 3, 24, plus 2 times 36. So that's 24 plus 72, 78. Looks like 98. Okay, let me double check that. 24 plus 72 gives me 76. Hang on. 24 plus 72. That's going to give me 96, not 98. Okay. All right. Now, it's clear now what the diagonal patterns are. The only thing that's not clear is this entry here. Okay. So let's see what we have here. We're going to have a to the n is equal to, certainly you're going to have 2 to the n on the diagonal. And then there's this entry here, which is kind of problematic. So let's look at an, and this is the first row, third column. So it's going to be equal to, first time it was equal to 3. Second time it was equal to 12. Next time it was equal to 36. And next time it was equal to 96. And this was for n equals 1, 2, 3, 4. Right now, it does seem a little bit difficult to discover a pattern here. But let's see if we can use some things that we already have here. Notice that we have the diagonal entries going as 2 to the n. So maybe we should think about 2 to the n figuring in here. So here I have an 1, 3. This one here is 3 times 1. Okay. This one here is, let's see let me factor out a 2. Okay, that's going to be 2 times 6. Here let me factor out a 4, and this is going to be 4 times 9. And here let me factor out a 8, and then I get 8 times 12. Okay. So instead of writing this as 3 times 1, I'm going to write it as 1 times 3. Okay, I'm just looking for patterns here. And if you didn't see this pattern with these 4, you could continue out farther. The reason I chose to factor out powers of 2 is that I had powers of 2 on the diagonal, so that seems to have something to do with a pattern here. Okay, so you can kind of see what the pattern here is. Here I have 1 times 3, so I can write this as 1 times 3 times 1. This 2 times 3 times 2. This is going to be 4 times 3 times 3. Then here I have 8 times 3 times 4. All right. So if we look at how this pattern works in general, what that tells me is this was n here. I'm sorry. This is going to be, this is a power of 2. This is going to be 2 to the 0 times 3 times 1. Then this is 2 to the 1 times 3 times 2. And then this is 2 to the 2 times 3 times 3. This is 2 to the cubed times 3 times 4. Now, how does this relate to n? That's the same as 2 to the n minus 1. I always have a 3 in all of them, and then here I have an n. Okay. So this pattern works for all of the ones that I have here, And you could continue on and see that, in fact, this pattern continues to work. So this result is what actually goes in the entry up here. So I'll write that here. This is going to be 2 to the n minus 1 times 3 times n. Okay. There's another way to do this that's kind of tricky, and I think it might be interesting to see how this works for you. I can write A in a different way. So here's a tricky way. Okay. So here I can write A as this. A is equal to 2, 2, 2, 0, 0, 0, 0, 0, 0, plus 0, 0, 3, 0, 0, 0, 0, 0, 0. Okay, so that's equal to 2i plus 0, 0, 3, 0, 0, 0, 0, 0, 0. Okay. Now if I raise a to the nth power, it's going to be the same thing as this 2i plus 0, 0, 3, 0, 0, 0, 0, 0, 0. I raise that to the nth power. Now I can pull out a 2, and that's the same as 2 to the n times I, identity matrix, plus 0, 0, 3 halves, 0, 0, 0, 0, 0, 0 to the nth power. Now let me call this little matrix here, I'll just call that A. Okay. So that's the same thing as 2 to the n times I plus A to the nth power. Now, this is a number, this is 2 terms to the nth power. I can do the binomial expansion. If you remember binomial expansion, x plus y to the nth power, there's a formula for that. That's equal to x to the n plus, next term is n, x to the n minus 1 y, plus, and so on. All right, if you don't know that, then that would be hard for you to come up with. But here I'm going to use my x is equal to I, and my y is equal to A. All right. Now you might ask, how do I know binomial expansion works for matrices? Well, because I'm just multiplying them together. Remember how this works is that you multiply out and collect terms. I can do the same thing with numbers as with matrices. In this case, I don't need to worry about commutative because I and A are commutative. I commutes with everything. So this is equal to 2 to the n times, it's going to be I to the n plus n times I times A, n times I to the n minus 1 times A plus and further terms. So these further terms have higher powers. So let's just say higher powers of A. Okay? So I can binomially expand out this sum of matrices raised to the nth power in this way. Now the neat thing about this is I to the n is I to the n minus 1 is A is A, and if you work it out, A squared is 0. So higher powers of A are all 0. All these terms are 0. Okay? So I'm only left with this expression here. Okay? So here I have, note that A squared is equal to, you can work this out, 0, 0, 3, 0, 0, 0, 0, 0, 0, or actually it was 3 halves, right? Is equal to 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? So the higher powers of A all disappear. For n greater than or equal to 2. Okay? All right, so what I'm left with is just 2 to the n times I plus NA. So my result is 2 to the n times I plus NA. Now remember what A is. A is 0, 0, 3 halves, 0, 0, 0, 0, 0, 0. So this 2 to the ni gives me 2 to the n's on the diagonal. And then 2 to the na, the a has a 3 halves here, so I'm going to get 2 to the n times n times 3 halves. Okay, and that's the same thing as what I got before, 2 to the n, 0, 2 to the n minus 1 times n times 3, 0, 2 to the n, 0, 0, 0, 2 to the n. So in summary, there's two ways to do this. One way is to look for patterns and try to generalize. Another is there's this tricky way of doing it. There's still another way that uses induction that I'm not going to talk about. But if you know something about induction, you can try to apply that and see how that would work in this case. Okay.